Have you ever felt like you're drowning in information? You know, like when you're trying to make sense of a ton of data and it's all jumbled up and you just wish there was some kind of magic trick to make it all click.
Yeah, totally. I mean, we see this everywhere, right? From teaching computers to actually see, like with self-driving cars, all the way to just getting our phones to understand what we're saying.
Right. And it feels like there's this whole hidden world of complex calculations going on behind the scenes.
Exactly. And a lot of that boils down to something called probabilistic inference. It's like this fundamental tool that helps us understand how likely different things are, especially when we have a ton of interconnected factors to consider.
Okay, so when you say probabilistic, you're talking about probabilities, right? Like the chance of something happening.
Exactly. It's all about figuring out probabilities. And to make things even more interesting, we often use these things called probabilistic graphical models, or PGMs for short.
PGMs. So what exactly are those?
Well, think of them as visual maps. They show us how different pieces of information, or variables, relate to each other and how they influence each other's probabilities.
Ah, okay. So they're like these maps that help us visualize the connections between different probabilities.
Exactly. And researchers have been using these PGMs for a long time, especially in fields like computer vision, robotics, natural language processing, you name it. Like Wang and his team used them to help computers understand images. Dillert and Kais applied them to robot navigation. Chater and Manning used them in natural language processing. And even Darwich, who works on causality, relies on them heavily.
Wow. So these PGMs are like the Swiss Army knives of probabilistic reasoning.
You could say that, but there's always a catch, right?
Uh-oh, there's always a catch. So what is it? What's the challenge with these PGMs?
Well, the challenge is that when you have lots of variables, it can become really computationally expensive to actually use these PGMs to do inference, to figure out the probabilities we're interested in.
So even though we have these maps, actually navigating them can become a huge problem.
Exactly. And one of the most common ways to perform this navigation, to do inference, is to use an algorithm called variable elimination, or VE.
Variable elimination. Okay, so what's that all about?
Basically, it's a step-by-step process for simplifying a PGM. You strategically get rid of variables, you eliminate them to make the calculations more manageable.
That sounds logical. Simplify, simplify.
Right. But here's the thing, and this is where it gets tricky. The efficiency of variable elimination really depends on the order in which you eliminate those variables.
So it's not just about eliminating variables, it's about eliminating them in the right order.
Exactly. Choose a good order, and everything goes smoothly. Choose a bad order, and you end up with a computational nightmare, especially as the number of variables grows.
A computational nightmare. I can already imagine the error messages popping up. So how do we find this magical good order?
Well, that's the million-dollar question. Unfortunately, finding the absolute best optimal elimination order is incredibly difficult. In fact, it's what computer scientists call an NP-hard problem, which essentially means that as the problem gets bigger, the time to find the perfect solution explodes exponentially.
Exponentially exploding computation time. That doesn't sound good at all.
Yeah, not ideal. So in practice, what people often do is use heuristics, these rules of thumb, to try and find a reasonably good order. But heuristics are just educated guesses. They don't guarantee the best solution.
Right. They're just trying to avoid that computational nightmare as best as they can.
Exactly. And that's where this deep dive comes in. We're exploring some really cool research that's taking a totally different approach to this problem, borrowing ideas from a seemingly unrelated field.
Ooh, borrowing ideas. I like that. So what's this other field?
It's called tensor networks. You can think of them as a way of representing data, particularly high-dimensional data, using these multi-dimensional arrays called tensors.
Okay, tensors. I vaguely remember something about those from linear algebra. But how do they relate to our PGMs, our maps of probabilities?
Well, it turns out there's this fascinating connection, or duality, between PGMs and tensor networks. You can kind of translate between the two worlds.
Oh, interesting. Tell me more about this translation.
So you can think of the random variables in our PGM as corresponding to the indices in a tensor network. And those factors we talked about, the ones that define the relationships between variables in a PGM, they're like the tensors themselves in a tensor network. Rebeva and Segal actually did some really cool work exploring this duality back in 2019.
So it's like we're looking at the same underlying structure, but through two different lenses. The world of probabilities and the world of tensors.
Exactly. And the cool part is, this connection opens up a whole new avenue for solving this elimination order problem. Because you see, in the world of tensor networks, they have a similar problem of finding the optimal order for performing certain calculations, called contractions.
Okay, so we've got these two worlds with similar problems. And what have the tensor network folks figured out that we can borrow?
Well, a group of researchers, Miram and his colleagues, came up with this really clever idea of using reinforcement learning to find good contraction orders for tensor networks. This was in 2022.
Reinforcement learning, that's where you have an AI agent that learns through trial and error, right?
Exactly. It's like giving the AI a playground to experiment in and letting it figure out the best strategies.
So are we saying we can take this AI agent, this reinforcement learning approach, and apply it to our PGM problem?
That's exactly what researchers are doing. In fact, the research we're diving into today by Sagad Hamid and Tanya Braun from the University of Minster explores exactly that. They're taking this reinforcement learning magic from tensor networks and adapting it to find better elimination orders for PGMs.
Very cool. So we're using AI to help us untangle those messy probabilistic calculations. But you also mentioned something about structure exploitation. How does that fit into the picture?
Ah, yes. This is where it gets even more interesting. So, typically when we're trying to figure out how good an elimination order is, we just look at the size of those intermediate factors that get generated during variable elimination. The problem is, these intermediate factors can still grow really, really big, even with AI finding us decent elimination orders.
So even with the AI's help, we can still hit a wall because the calculations become too massive.
Exactly. And that's where exploiting structure comes in. Hamid and Braun are suggesting that we can be smarter about this whole thing by actually looking at the internal structure of the factors themselves.
Okay, so it's like we're not just blindly eliminating variables anymore. We're taking a closer look at what's inside these factors.
Right. And the specific type of structure they're focusing on is called local symmetry.
Local symmetry, that sounds intriguing. What does that actually mean in the context of these factors?
Well, basically, a factor has local symmetry if you can swap around the values of certain variables without changing the output of the factor. It's like having interchangeable parts in a machine. But in this case, those parts are the variables.
Interchangeable variables. Okay, I think I'm getting it. Can you give me a real-world example?
Sure, imagine you have a factor that tells you the probability of a group of friends going to a movie. If the probability only depends on how many friends are free and not on which specific friends are free, then you have local symmetry. Because it doesn't matter if friend A is free and friend B is busy, or vice versa, the probability of the group going to the movie stays the same.
That makes sense. It's like the specific identities of the friends become irrelevant. It's just the overall count that matters.
Precisely. And the key insight here is that by recognizing and exploiting these local symmetries, we can represent those factors much more compactly. We don't need to store all the individual combinations, just the essential information.
Compact representations, that sounds like a good thing. Less storage space, less computational overhead.
Right. And to do this compact representation, they borrow an idea from an area called lifted inference, specifically these things called counting random variables, or counting RVs for short.
Counting RVs, what are those?
It's pretty simple, actually. Instead of keeping track of the individual states of each variable, we just count how many variables are in each possible state. So in our movie example, instead of saying friend A is free, friend B is busy, and so on, we just say there are two free friends.
So we're going from a detailed list to a summary. Much more efficient.
Exactly. Figure 2 in the paper really illustrates this nicely. They show a factor with 3 variables, and instead of having to list out all 8 possible combinations, they just use a counting RV that tells you how many variables are true.
Yeah.
It dramatically reduces the amount of information you need to store.
So we're essentially compressing the information without losing anything important. But now the big question. Can we still do those variable elimination calculations when things are represented in this compressed form?
That's the key. And luckily, the answer is yes. Hamid and Braun prove this mathematically in their paper. They show that the core operations we need for variable elimination still work perfectly fine, even with these compact representations.
Phew, that's a relief. So we're not just saving storage space, we're actually able to perform the computations more efficiently as well.
Exactly, and they even tested this out with experiments. They compared a computational cost of doing variable elimination with and without exploiting these local symmetries. And guess what?
I bet it was much more efficient with the symmetries.
You got it. Especially when they were working with factors that had these Boolean true or false variables, it was a huge improvement. And they found that considering these compact representations never made things worse, it only made them better.
That's really impressive. So by being clever about how we represent these factors, we can potentially make huge strides in making probabilistic inference more tractable.
Absolutely. And it's important to note that this is just one piece of the puzzle. Researchers are exploring all sorts of other ways to exploit structure for more efficient inference.
Really? What are some other examples?
Well, there's a lot of work on exploiting global symmetries. It's kind of like local symmetry, but on a larger scale. And then there are approaches that focus on isomorphisms, which are these structural similarities between different parts of the graphical model. Some researchers are also looking at ways to directly exploit the tensor structures themselves using techniques from linear algebra. And then there are approaches using things like Fourier representations, causal relationships, polynomial representations, even circuit-based representations. It's a really diverse and exciting field.
So the takeaway here is that by paying attention to structure, we can potentially unlock a whole new level of efficiency in probabilistic inference.
Absolutely. And this research by Hamid and Braun really highlights that point beautifully. By combining reinforcement learning with structure exploitation, they're showing that we can teach AI to not just blindly try different elimination orders, but to actually see those efficiencies hidden within the structure of the factors themselves.
So it's like the AI is learning to be a more insightful problem solver.
Exactly. And that's something we can all learn from, even beyond the world of probabilistic inference.
It's really inspiring to see how these seemingly abstract mathematical concepts can have such a big impact on how we solve real-world problems.
Definitely. And the key takeaway for you, dear listener, is to remember that structure is everywhere. It's in our data, it's in our problems. And by paying attention to it, we can often find those elegant, efficient solutions that might have been hidden in plain sight.
It's like we need to train ourselves to see beyond the surface complexity and look for those underlying patterns, those opportunities for simplification.
Couldn't have said it better myself.
So the next time you find yourself facing a daunting problem, remember this deep dive. Ask yourself, where might the hidden structures lie? What are the counting RVs in your own challenges? How can you leverage those insights to find more efficient solutions? It's a powerful way of thinking that can be applied to so many different areas. And if you want to delve deeper into the fascinating world of probabilistic graphical models and structure exploitation, we highly recommend checking out the research we discussed today and exploring the wealth of knowledge out there. It's a journey well worth taking.
Agreed.
Until next time, happy exploring.
See you then.